We're going to start now a session on video analytics, and our first speaker is Dan Xu from University of Oxford.
Good morning, everyone. I will present our work, geometry-aware video object detection for stair cameras. This is joint work with Weidi and Andrew in VGG group at the University of Oxford. So object detection in under static cameras is a very important research direction due to the increasing number of cameras deployed in smart cities. There is also a wide range of application scenarios, such as video analysis, video surveillance, as well as self-driving, in which the cameras could be also approximated in a static setting. And in this work, we focus on videos such that the important spatial-temporal constraint could be fully explored and employed for learning an effective object detector. And specifically, we consider object detection on two specific classes, namely the vehicle and the pedestrian classes, which are two most common classes in our real life, especially in various video analysis applications. Although great success has been made in recent years in video object detection, there is still open challenges in this task, such as the scale issues. The researchers have been trying many different ways to solve this issue, such as designing multi-score network structures or utilizing different data augmentation schemes. However, this issue has been only partially solved. An essential reason of failure is that the 2D images basically lose the important geometry information during the projection from the 3D world. However, the geometry information, such as depth, is very beneficial to handle the scale ambiguity problem. We know that the further the object is from the cameras, the smaller the object is. As shown in Figure C, the pseudo depth map can be estimated from the object height on the image plane. And under static cameras, we can estimate such as same geometry information. So in this work, our contribution is twofold. The first is we propose an anchor-free spatial-temporal detection architecture. And the second is we propose a geometry-aware module for learning effective deep representations and also the network prediction. In the next of my talk, I'll firstly simply review a recent anchor-free single-frame object detection architecture called NET, and then produce the details of the proposed network architecture. And then I will introduce our experimental settings and the corresponding results. And then finally, I'll summarize. So to overcome the complexity of the object detection in two-stage setting, so the rest of the work, CornerNet, proposes a one-stage anchor-free detection pipeline. We know that two corners can determine a bounding box. Through learning the corner prediction and the association between the corners, we can predict the object bounding boxes. They actually use focal laws for the heat-map regression, and then use the contrastive laws for learning the association between the corners. After they have the heat-map and the corresponding heat embeddings, they could predict object class on the image plane. So to fully employ geometry information and also simplify the detection pipeline in the video setting, in this work, we mainly explore two things. So the first thing is a one-stage detection architecture based on spatial-temporal features and anchor-free detection pipeline. And then the second thing we want to explore a geometry-aware module which could be embedded in any deep learning networks for learning effective deep representations and also its final network predictions. So in the next, I will introduce the details of the proposed approach step by step. So the network accepts multiple frames as input, and we pass them into a spatial-temporal 3D convolutional backbone, such as a C3D or ResNet 3D network structure, to obtain spatial-temporal representations. And we also consider deriving multi-scale representations from the backbone. So for the geometry input, we consider both the 2.5D pseudo-depth map and also the 2D coordinates map. The pseudo-depth map could be estimated from the training data directly. And for each row on the pseudo-depth map, the depth value is calculated by the mean of the maximal and the minimal height of all the bounding boxes of all the objects on the image plane. Since the geometry input is very coarse, because it's directly estimated from the training data without any parameters learned, so we want the network to learn a more fine-grained the geometry representations. So we perform a nonlinear transformation based on the geometry input, and the nonlinear transformation is performed by using two stacked convolutional Bachelon ReLU blocks. After we obtain the fine-grained representation of the geometry input, we produce a set of attention maps, the geometry-based attention maps, and these attention maps will be further used to select the multi-score representations we obtained from the backbone network structure. The motivation we want to use the geometry to guide the selection of the multi-score features is that we want to select the shallow representations for the small-scale objects, and we want to select deeper representations for the larger-scale objects. And this multi-scale feature selection is performed by using linear combination with all these multi-scale features and using the learned geometry-based attention maps as weights. For the network prediction, we predict, because our input is a multi-frame video clip. So we predict for the first frame and the last frame with the shared the video representations to have the spatial constraint on the feature level. And we also consider to jointly use the geometry representations and the video representation for the prediction by concatenating them. So for the normalization of the whole network, we use the focal loss for the regression of the corners for the first frame and last frame. And we also use the contrastive loss to learn the association between the corners. And the whole network can be optimized in an end-to-end fashion. So to evaluate performance of the proposed approach, we'll consider two different data sets. The first one is a synthetic data set. We collected it using a self-driving simulator color, and it contains 48 different scenes of long videos, and we use 40 scenes for training and the rest for testing. It has both the vehicle and the pedestrian classes. The second data set we consider is a Duga TMTC data set. We use the video data from the camera 125, and it has only the pedestrian classes, the pedestrian class. To evaluate performance, we use three different evaluation metrics. The AP50 and the AP75 are the average precision at IOU 0.5 and IOU 0.75 respectively. And the MAP is a mean of AP50 and AP75. So this video shows some qualitative examples on both datasets. The white blobs predict corners of the bounding boxes. And our approach could achieve good results on the detection objects in a diverse of scales. To further validate the effectiveness of the different proposed skins, we did a detailed avalanche study on the color data set. So to compare the single frame corner net and our base network, the GusNet multi-frame, we improved 9.39 points. So it's a very significant improvement over the single frame detection framework, corner net. So this clearly demonstrates the effectiveness of the designed spatio-temporal detection structure and also the learned video clip representations. So by further using the 2.5D pseudo-depth map in the network prediction as we discussed, so we have like more than 3 points gain. So this shows that the pseudo-depth map information is very useful for the network prediction. Even you just add this as a final prediction layer. So by further using the learned fine-grained geometry distribution to select the multi-score features, we have more than 4 points gain over the third baseline. And in total, by using geometry information for the feature selection and the network prediction, we have more than 7 points over our baseline GusNet multi-frame. This improvement clearly demonstrates that the geometry information is very beneficial for the detection problem. We consider different backbones on the Ducat TMTC datasets, and we significantly outperformed fast RSN, SSD, and single frame corner net on MAP. And we also achieved a much better performance at ILU 0.5. It shows the more accurate localization ability of the proposed approach. So to summarize, in this work, we propose a geometry-aware spatial-temporal network for video object detection. It's a one-stage, anchor-free. And we have showed great advantage of using geometry information in deep networks for learning both the feature representation and network prediction. And it's also potentially beneficial for other related computer vision tasks which could be affected by scale issues. Thank you.
Okay, any questions? Okay, let's ask in the other room. Are there any questions?
No, there's nothing on this side.
Okay, well, let me ask you a question.
Okay.
So you mentioned that you did you have some rather low quality depth estimations, so you do some nonlinear transformation to improve the quality of the resolution. I didn't quite understand how does that happen? How do you do it? Okay.
Actually, for the geometry information, we don't use the exact depth sensor to give us the geometry information. We want to because our assumption is we're based on static cameras. So based on static cameras, we can actually estimate the depths of the objects in this thing. So, but this estimation is cost. Yep. So if we have parameters, deeper parameters to learn a more accuracy, of course we also need to, based on the final loss, the detection target. So when we have a small network to learn embedding from the coarse geometry input to have fine-grained representations of the geometry input, this could improve the performance. Yes.
Okay, thank you.
Yes.
Right, well, we better move on. So thank you again very much. If the next speaker can come up, please. And so our next speaker is Gursimran Singh from UBC.
Thanks for the introduction. I'm Gursimran. So I'm presenting my work today titled Spatio-temporal Relational Reasoning for Video Question Answering, which I did jointly with Leonid, Sigal, and James Little at the University of British Columbia. So what is video question answering? It's a task of answering a natural language question on video. And here are some examples on the two datasets which I consider in this work. So existing approaches used a combination of CNNs and LSTMs. However, LSTMs are known to not work well for long sequences, especially when those sequences contain information-rich data like frames instead of words. Second, they don't provide any prior knowledge, which means that they have to learn the spatio-temporal reasoning from scratch. To remedy this, temporal relational networks were proposed, and which used relation networks which act like an effective prior to capture relations among frames of a video. However, the problem was that they only capture they capture relations only in the temporal domain, and they don't provide any way to capture spatial relationships of possible objects inside a frame. So we extend this work to capture both spatial and temporal relations jointly. So to understand how we work, let's consider this example. So the question asks which object moves closer to the blue cylinder. So how we deal with this is we randomly consider two objects in this, and then we compute spatial relations among these objects in each frame independently, which is far in the first frame, close in the second frame, and closer in the third frame. Then we simply see how these spatial relations evolve over time. And then we call these the evolving thing of spatial relations as spatio-temporal relationships. And then we consider these spatial temporal relationships among all possible objects, and having observed that, we can arrive at the final answer, which is sphere in this case. So that's the outline of how we want to approach this problem. And here is the proposed architecture of spatio-temporal relational network. It has 3 different modules, which I'll discuss in detail in the following slides. The first one is spatial relation module, which captures the spatial relationships among objects, which may be present in any frame. The input to this module consists of CNN feature maps, and which are reduced in size using a downscale CNN for computational reasons. Next, we consider all possible pairs among the CNN feature maps as possible objects, along with the quotient embedding gamma. An important thing to notice here is that we don't have any explicit representations of objects, and we simply treat CNN feature maps as a loose sense of object, which might capture an object which span its area in the image. Then we simply take all these combinations and we pass these combinations through a spatial relation function, which is d theta s, which is nothing but a multi-level perceptron. And it can actually capture arbitrary relationships, which it can learn from when we train it using data. Finally, another function, which is h phi s, it simply reasons over all the relations and do the second level reasoning over it. So overall, we can see that this module captures object interactions in each frame independently. Next, we have the temporal relation module. So temporal relation module takes embeddings from the spatial relation module, and each of these embedding basically has the information of possible relationships inside a frame. And similarly, we have the temporal relation function, which is g alpha t, and the reasoning function, which is h beta t, which basically computes all possible relationships among the frames and reasons over them in the end, which is similar as I described earlier. The only main point which is different here is that how we treat the possible object pairs over here. So because this is temporal domain, we don't simply consider all possible pairs. Instead, we only consider pairs which follow in time, which means that if there are 2 pairs A and B, then the pair B will always come after the pair A. The frame B will always come after the frame A, and it won't be the vice versa. So overall, we can see this as capturing the relationships among the spatial relationships, which means that we are seeing how the spatial relationships are evolving over time. And the next thing is global context encoder LSTM. So earlier we captured object interactions. However, what was missing was the action dynamics of individual objects inside the video, which means that if I have a hand, how my hand is evolving over time. So in order to capture this, we leverage 3D CNN feature maps, which basically contain motion information, local motion information of individual objects inside the video, inside that frame or around that frame. However, since the information is local, we pass these frames inside through an LSTM to make it global and add global context to it at time t. So then we pass this embedding to the temporal relation module, and we can see this as capturing time-changing action dynamics of individual objects inside the video. So let's do a quick recap because there was a lot of stuff over here. So first of all, the spatial relation module, it captures the object interactions among inside the frames independently. The global context encoder LSTM, it captures action dynamics of individual objects. And when we pass these two together inside the temporal relation module, it basically captures the object interactions and also the action dynamics and see how it changes over time. Finally, we use this embedding and we pass it through the answer decoder module, which is consistent with the previous work, which either does regression in case of questions which output a number, or it does a classification where it has to choose from a list of answers. Okay, let's go to experiments now. So there are two data sets which we consider, TGIF-QA and SVQA. And these are the instances of them. I don't have the question over them, but you see in the you saw that in the first slide. So the TGIF-QA contains real-world videos like that, and synthetic SVQA dataset has these synthetic videos where you have certain objects. And so both these datasets have different categories of questions, which include counting, transition, and comparison, etc. The evaluation metric that we use is just consistent with the previous work. We use mean squared error for question types which output a number, which is the count task of TGIF-QA, and we use classification accuracy for all other tasks, where we just simply pick one of the options. So let's first consider comparison with state of the art on TGIF-QA dataset. Here we consider 4 different tasks. And the upward arrow means that the higher is better, and lower arrow means lower is better. So these are the image-related VQA baselines. These are the video VQA baselines, which are the current state of the art. And this is our approach. So as you can see, our approach considerably beats the existing approaches. The only task where it does not perform better is the frame QA. And the argument over there is that frame QA does not even require spatio-temporal reasoning, because the answers can be, because the question can be answered by just looking at one single frame of a video. And the approach which performs best over there is the self-attention based approach, which are known to do better in case of image-based VQA as well. The other thing which I would like to highlight is the count task over here, where we get a substantial improvement of around 4.5%. For 4.5% than the next best baseline, which is considered as a very challenging task in video question answering. Similarly, we have the comparison with the state of the art on the SVQA dataset. It has a lot of numbers. The things which I want to point out is that we get around like 2.5% overall better than the next best approach. And again, we have like a substantial improvement of like around 6.5% in the challenging counting task, where you have to count the number of times a certain event happened in the video. Here are some ablation studies, so basically the aim of the ablation study was to understand the importance of joint spatio-temporal reasoning as opposed to just the temporal or just the spatial relational reasoning over there. And as we see, the joint spatio-temporal reasoning network beats the other two considerably, and the next best thing is just using the temporal relation network, which also does quite decently. Here are some qualitative results where our approach gets the correct answer, and the one of the recent works by Jangho et al., it could not get the correct answer, just for illustration purposes. Of course, cherry-picked. And again, I have some qualitative results on SVQA. Okay. And yeah, conclusion. So we present a novel general-purpose neural network module, which provides an effective way to model spatio-temporal relations. And so this captures both object interactions and action dynamics inside the video. We demonstrate the effectiveness of this on a variety of video QA tasks for both real-world and a synthetic data set. And we believe that this can be extended to other video understanding tasks as well. And more importantly, we obtain a substantial improvement on the challenging counting task. Thank you.
Questions?
So what do you think that improvement in counting?
Just wait for the mic, please.
As you pointed out, the substantial increase in the counting.
Yeah.
What do you think? Which part of the network is responsible for that? If you want to point out something.
So I think this is mainly due to the relation networks. So earlier, people are using a combination of LS teams, either memory networks, or they are trying to use self-attention based, which does not provide an effective prior to, model relationships among the videos. And counting is like a complex relationship where you have to sum up all the events which are happening. So that's why our network is able to perform better, like significantly better than earlier approaches.
So in the real world data set, TG, whatever it was.
TGIF, yeah?
Yeah. Do you think there were any scenarios where there was an object that was going out of the scene, so then in the subsequent frames of the video, it was not there? So without a module like object tracking or activity recognition, it was getting difficult for your model to reason about or to answer those kind of questions which revolve around the tracking?
So I particularly did not notice any such instance, but it's like quite in the wild data set. I mean, there might be such instances. I'm actually not sure about this.
Okay. Something to think about.
Yeah, okay. I think that's a good point, actually.
Okay.
Okay, just quickly check. Anyone in the other room with a question?
No, there's nothing on this side.
Is it a quick question? Yeah. Okay, go on then.
Can you go quick to the slide with all the results that you had on the last data sets, the big table? Yes.
This one?
So yes. So I see there that the actual part in which your network is weaker is in the attribute comparison part. So it's, for example, here you lose 7% on one part, you lose 3% on type or 3% on shape. So does this mean that your network is pretty weak on appearance embedding actually? And could you think that you could improve this, like maybe plugging some object detection approach that try to enforce in some part of the image some kind of more appearance-related features?
So certainly, I think there are points of improvement, and certainly if we add concrete representations of objects, like by using bounding boxes or object detectors, we are definitely going to do better than using abstract CNN feature maps. But one advantage of relation networks is that they can work with abstract representations as well, as opposed to graph neural networks. So regarding this particular comment, why does it perform worse in attribute comparison? Actually, I don't know and haven't done much analysis, but I think it's like a really important question to understand which approach work where, and we need to do like a more controlled study to understand that.
No. Okay,
yeah.
Thanks.
Thank you. Okay, so our next speaker is Jungbeom Lee from Seoul National University.
Good afternoon, everyone. I'm Jungbeom from Seoul National University, and I'm here for presenting our paper, Mutual Suppression Network for Video Prediction using Disentangled Feature. This is the joint work with Jangho, Sungmin, and Yoon. This was supported by Ministry of Science and ICT of Korea, Samsung Electronics, and Brain Korea 21 Plus project. Okay, let's get started. Given these videos, can you predict what would the next several frames look like? This is what we exactly would like to do in this paper, which is called video prediction. Video prediction has several applications for such as CCTV and self-driving cars. Additionally, some works use video prediction for unsupervised learning of image representations. As everybody here can guess, video prediction is a very difficult problem. It is because that video has not only high-dimensional spatial information, but also complex temporal information. Rather than modeling these two complex factors together, we disentangle motion and content component. We here introduce Mutual Suppression Network, which is called MSNet. MSNet disentangles motion and content information by suppressing each other, and it can be realized by adversarial training. Our overall procedure consists of two stages. The first stage is frame reproduction task to learn disentangled features. And with these disentangled features, we perform the frame prediction in the second stage. In frame reproduction step, MSNet learns to disentangle motion and content in a self-supervised manner. Given three frames x1, x2, and x3, the content from x1 and x2 and the motion from x2 and x3 should be able to reproduce x3. In this task, the motion and content encoder can learn to generate disentangled features, and these encoders are used in the next stage. The second stage is frame prediction. The encoders trained in stage 1 are used for frame prediction in this stage. Let's check more details about these two stages. MSNet consists of motion encoder and content encoder. As I said earlier, content is extracted from xt and xt plus 1, and the motion is extracted from xt plus 1 and xt plus k. And the combination of these two features should be able to reproduce the last frame xt plus k. Here, we use U-Net-based architecture, which has skip connections in each convolution block. However, the direct connection from previous frames to target frames may be very harmful. So we propose motion-guided connection here. In each connection, we use motion information obtained in here by motion encoder to modify the spatial information from previous frames. By doing this, more meaningful information is conveyed from previous frame to the generator, so it can reproduce more reasonable target frames. Here is loss functions to optimize MSNet. MSNet is trained in adversarial manner by optimizing L1 and L2 in turn. The first loss function is reconstruction loss. It is just mean squared error loss to reproduce frame xt plus k from content of xt, xt plus 1, and the motion of xt plus 1 and xt plus k. The second one is time reversal loss. The content encoder gets two frames as an input, which some temporal information can be unintentionally included in content feature. We use this loss so that the content encoder can generate the same result when the order of input is reversed, which means content encoder is not sensitive to temporal order. The next one is frame adversarial loss. We use adversarial loss like pix-to-pix method. This loss gets a pair of xt and xt plus k or xt and generated xt plus k. With this adversarial training, we can obtain more realistic xt plus k. The remaining loss functions are designed for disentangled content and motion. We can obtain pure motion features by suppressing content features with these two loss functions. We define content discriminator TC. Given the two different videos, video X and video Y. When the two motion features obtained from the same video, content discriminator is trained to classify it as same. When the motion features obtained by different videos, content discriminator is trained to classify it as not same. In order for this to be possible, the content discriminator should be able to discover content features in given motion features. That means motion features contain the content information. Now, motion encoder is trained to deceive the content discriminator. So the motion encoder is trained to generate motion features that contain as little content information as possible. It is very similar to obtain pure content features by suppressing motion features. The motion discriminator gets a single content feature and check if the content feature is obtained from sequential frames like here, XA plus XA plus 1, or non-sequential frames, XA or XB. In order for this to be possible, motion discriminator should be able to discover temporal information in given content features. That means content features contain motion information. Content encoder is trained to deceive motion discriminator so that it can generate content features that contain as little motion information as possible. The content and motion encoders trained in frame reproduction task is used for frame prediction here. The motion features are predicted using convolutional LSTM, and the predicted motion features are used to generate the future following frames. Let's discuss experimental results now. We use two datasets for evaluation, moving MNIST and KTH dataset. More details about dataset and experimental settings can be found in the main paper. This is the result of frame reproduction task on moving MNIST dataset. Compared to DRNet, which is very powerful baseline, we can see that our MSNet can generate more reasonable frames. DRNet sometimes have difficulty for overlapped digits like here, or swap the location of two digits like here, or DRNet sometimes generate blurred outputs. We attribute this to the better disentangled features obtained by MSNet than DRNet. Here are the results of predicted frames by ours, DRNet, MCNet, and FRMN. As you can see, our method predicts more realistic and reasonable frames than strong baselines. Okay. Here are the other examples of predicted frames. Again, our method generates more realistic frames than strong baselines. We present quantitative results on the KTH dataset here. This figure and table show the comparison with state-of-the-art method. As our method can get well disentangled features, we have a good starting point here. And our method shows less performance drop than other methods through time steps. This is the average performance over predicted 20 frames. Our method shows the best results among the baselines. In ablation study, to show the effects of mutual suppression on the disentangled features, we removed each discriminator in turn. In this figure, for blue and gray one, the performance drops significantly through time steps because they have no content discriminator, so that they fail to obtain pure motion features. For green one, the performance dropped not too much because it had pure motion features, but it has bad starting point because it had no motion discriminator, so that they fail to obtain pure content features. The table shows the average performance over predicted 20 and 30 frames. Note that here MGC denotes motion-guided connection. Here, we can see the effect of our contributions. It is the TSNE visualization of dynamic actions and static actions. Dynamic actions contains walking, jogging, and running, and is denoted by red points. Static actions contains boxing, hand clapping, and hand waving, and is denoted as the blue points. The first row shows motion feature visualization, and the second row shows the content visualization. In an ideal case, motion should be clustered and content should be randomly dispersed. We can see that MSNet with both discriminator here first shows the most ideal situation. MSNet without motion discriminator in the second column has pure motion features, so it shows clustered aspect in this motion visualization. MSNet without content discriminator in these two settings, it fails to obtain pure motion features, so it shows dispersed aspect in here. In the second row, MSNet without motion discriminator in the second column, it fails to obtain pure content features. That means content feature have some temporal information. So we can see the clustered points in here. It's time to wrap up my presentation. We have proposed a mutual suppression network to disentangle motion and content. We also have proposed motion-guided connection in encoder and decoder-based architecture for conveying information more effectively by skip connection. With these contributions, MSNet can obtain well-disentangled features, and it was shown in the experimental result. Thank you for your attention. Feel free to ask about my presentation.
Hello, thank you for your presentation. I didn't notice, can you show some examples where your method failed, where you don't manage to predict following frames?
Sorry, say again.
Can you show some examples where your method fails?
Fails? The failure case is shown in the main paper, but I was not present in this presentation, so you can check our main paper.
And can you describe in a few words what is the use case of it, like activity, or what is the kind of activity, or?
Actually, it is for all methods in these days. Small actions or small objects can be failed to predict following frames. So, for example, in the third row, starting from small object, it fails some in all methods. So I think it can be further improved in the following method, in the future method.
Okay, thank you a lot.
Thank you.
Any questions in the other room?
No, not on this side.
Any other questions? Okay, one more question up here. So, what the variant?
Thank you. A variant of the previous question. What happens after, let's say, 100 frames?
100 frames? Actually, we haven't tried that, but in this case, after, for example, in this case, after people are going to the corner of this frame, and maybe it is just background after these figures, I think. And in this case, because 20 or 30 frames can be predicted effectively, so I think it can work well with these examples, I think.
So will the arms go up again and then back down and then back up and then?
Sorry?
Will the person moving the arms?
We think that I was not explained in this presentation, but our network is on the hierarchical prediction. But in this example, MCNet get the output of predicted frames as input. So our network is robust to the error of previous frames. So we can more effectively predict the more future frames than this method, I think.
Thank you.
Thank you.
Thank you. Thank you.
Okay, our next presentation is Dimitrios Kollias from Imperial College.
Hello, good afternoon. Now I will present you the paper entitled Expression, Affect and Action Unit Recognition of While 2 Multitask Learning and ArcFace, co-authored by myself and Stefanos Zafeiriou. The rise of deep learning models as a means to address any computer vision task brought the need to collect and annotate diverse datasets. In this paper, we target developing deep neural networks for affective computing. The affective computing has been largely limited in terms of available data resources. In particular, we propose a unified approach to the problem of facial expression recognition, including valence and arousal estimation. Valence shows how positive or negative an emotional state is, whereas arousal shows how passive or active it is. Basic expression classification. This is classification to the 7 basic expressions: anger, disgust, fear, happy, sad, surprise, and the neutral state. And facial action unit detection. In total, there are 44 action units. In this paper, we will mainly target 8 action units. Lab-controlled databases were used for affective computing in the past. In recent years, some, but not many, in the wild databases were generated, including the AffectNet. This is a static database, contains annotations for valence and arousal and the 7 basic expressions and the contempt. The problem with this database is that it contains only 350K out of the 1 million images that contain valid faces and are manually annotated for valence and arousal. And as I said, it's a static database. This means that it contains no video, neither audio. Another database is the Emotionate one. Again, this is a static and database. It contains annotations for 11 action units and the 6 basic and 7 compound expressions. The problem with this database is that it contains only 50K out of 1 million images that are manually annotated for action units. It's static again. And less than 3K images are manually annotated for expression, making it really difficult to train deep neural networks on this database. Also, the categories are imbalanced. The last is the AFWILD database, which is the largest audiovisual database, contains 1.25 million frames, and it contains manual annotation for valence and arousal. The problem is that it contains only valence and arousal annotations. So in this work, we extend this database to cover all 3 main problems for FAIR. We develop appropriate deep neural networks that are multitask, multi-domain, and multimodal for FAIR. We adopt and use a news-loss function for basic expression classification, and we present an extensive experimental study to validate our developments. The first contribution, as I said, is the development of AVWILD2. This is the first database that is annotated for all behavior tasks. This is the first database that contains action unit annotations for audiovisual inputs, and it is the largest in the wild database, containing 2.8 million frames, consisting of 558 videos. In the figure, you can see some frames from the AVWILD2, and there are people displaying a lot of different emotions. You can see different poses, professions of people, illumination conditions, and occlusions. In total, the AVWILD2 database contains 458 subjects, 279 are male, 179 are female. The 558 videos consist of 2.8 million frames are annotated for valence and arousal. 63 videos with 400K frames contain annotations for those action units. It's 8 action units that have to do mainly with the inner, the outer brow laser, the action unit for the mouth and for the cheeks, and the lips part. And 84 videos contain annotation for the 7 basic expressions consisting of 404K frames. Here you can see some properties for the ArcWile2 database, and you can also see the statistics for the annotation for valence arousal, the expressions, and the action units. The second contribution is the development of multitask, multi-domain, and multi-class CNN models based on the sphere phase with 20 layers, the inception resonant, and the VGG phase. Here you can see the VGG phase, 2 fully connected layers of 496 units, and the output layer linear for valence and arousal. The action units are extracted from the sigmoid, and the expressions are extracted from the softmax layer. Another contribution is that we developed multitask, multi-domain, and multi-class CNN and RNN, because in the previous case the VG phase provided the best results, as we will show in the experimental section. We based on this for the development of CNN and RNN. As you can see, it's the convolution and pooling parts of VGG phase, followed by one fully connected layer, and on top of that we stack a 2-layer GRU. Each layer has 128 units. We also built multitask, multi-domain, multi-class, and multimodal CNN RNN. As you can see, this is an early fusion of 2 networks. The fusion is performed through a GRU layer, a 2-layer GRU actually. And the 2 layers, each one consists of the visual input. The other is from spectrograms, which are extracted from the audio. And all developed networks that we have presented till now are trained on the ArcWile2 and then tested on 10 publicly available datasets. The ArcWile, the FUVA, AffectNet, RAFDB, FAIR 2013, IMFDB, the Emotionnet, DISFA, BP4D Spontaneous, and BP4T+. In the previous networks that we described, the loss function was the sum of the categorical cross entropy, the binary cross entropy, and the concordance correlation coefficient-based loss. Now, for facial expression classification, we use a new loss function. It's the ArcFace loss, which was designed for face recognition. Let's note that this is the first time that the loss targeted for face recognition, we use it in the motion recognition domain. And just to see a little this loss, we rewrite the softmax cross entropy, as you can see. In the ArcFace loss case, what we did is that we add an angular margin penalty between the W and WYI and the XI, the M. And we also designed 2 networks. We trained with the ArcFace loss and test them on various emotion databases. These are the 2 networks, is the multitask ArcRes and the ArcVGG. The ArcRes is a network with embedding layer. The FC that you can see in the figure is the embedding layer, and it's based on residual units. The difference, the empty ArcVGG, is that in the figure, in the rectangular area, it's just the VGG phase instead of the residual units. As far as pre-processing is concerned, for the visual modality, we detect the faces through the SSH detector. We align the faces through the use of 5 facial landmarks. We resize the cropped faces to dimension 96 times 96 times 3, and we normalize the pixel intensities in -1. As far as the audio modality is concerned, we sample the audio signal mono at 44.1 kilohertz. We extract spectrograms. For the spectrogram frames, we computed them over a 33 millisecond window with 11 millisecond overlap. And in order to be consistent with the preprocessing of the visual modality, we normalize the spectrogram's intensity values in -1 and 1. Experimental results now. So in the evaluation matrix is the concordance correlation coefficient for the valence and arousal, and for expression classification is the F1 score, except the RAFDB, which the default evaluation metric is the mean diagonal value of the confusion matrix, and the FAIR 2013, which the default is the total accuracy. So the first table you can see a comparison between the multitask and the single task networks. As you can see, the multitask networks that we developed outperform the single task networks. In the second table, you can see a performance comparison between the multitask networks and state-of-the-art methods, and the multitask network had a superior performance than the state-of-the-art. The only exception is the AffectNet database. Next, we present 2 more tables. One has to do with comparing the developed architectures with the state-of-the-art for valence and arousal estimation. The other table has to do with for action unit detection. In all of those cases, with the exception of BP4D Spontaneous, that our performance was a little worse than the winner of Ferrat, our networks outperformed the other methods. And this is for the case that we used the new ArcFace loss that we introduced. As we can see again, the ArcRes, the multitask ArcNes, and the multitask ArcVGG outperformed the other competitors. Conclusions. The AVGUILE2 constitutes a very rich database for deep network training and further testing on very different diverse emotion datasets. The presented cross-database results validate our network developments, and the ArcFace law is beneficial for expression recognition. For future work, we extend the annotation of AVGUILE2. As a matter of fact, we are currently extending the annotation so that to contain more videos with basic expression annotation, with compound expression annotation, with speech annotation, and with attention of the subjects in the videos. And we will probably run related challenges a workshop in the next Face and Gesture conference. Thank you.
Let me just ask a question.
Sure.
You refer to some of the other databases as being imbalanced, but is your database surely still unbalanced?
It depends on what you say. So for the Vincent arousal, of course it is imbalanced because as you see the 2D motion wheel, so this is valence and this is arousal. So negative arousal, we don't have a lot of videos because in reality you cannot find. I mean, people are not uploading videos or showing themselves when they are negatively aroused. Yes. So for the expressions, I mean, I have the distributions here. They are in balance, which is also the case, but not that much, because I guess you are referring to the case of Emotionet, and this is because it's like 3,000 images, and it's 16 categories. So it's like if you do the average, which is not an average, it's like maximum 100 per category. Yes.
Let me ask in the other room, are there any questions?
No, there are no questions on this side.
No. Okay. Last chance, any questions? Okay, thank you again.
Thank you too.
Okay, so now we move on to Harshala Gamula from QUT.
Hi everyone, I'm Harshala Gamula from Queensland University of Technology, Australia. So today I'm going to present our paper, Forecasting Future Action Sequences with Neural Memory Networks. So this work was done with the collaboration of Dr. Simon Denman, Professor Rida Sridharan, and Professor Clinton Fuchs. So in this task, we consider input videos which contains multiple actions. So when given the video, we consider only a small portion from the earlier frames. So then we aim on predicting the sequence of plausible future actions. We believe such long-term predictions of activities is more beneficial, as there is strong potential for such systems to be used in real-world tasks, such as in warning systems in security or healthcare facilities. Let's first review the current state of the art for this task. So, to the best of our knowledge, this is the only existing work we have. So, they're the one who introduced the problem of future action sequence prediction. So, in this baseline method, the authors have introduced the future action sequence prediction task, anticipating the activities that occur within a time horizon of up to 5 minutes, with the aid of 2 models. So in the first model, which is the RNN network, it is based on utilizing the sequence of action labels along with their durations, and then pass them through 2 layers of RNN to obtain the predictions of future actions. So in the second model, which is the CNN model, they encode the sequence of action labels to a metric representation and apply convolutions on top of it. So, however, we believe when using only the action labels, we are unable to capture other vital information such as objects in the scene and their long-term dependencies. Among our main contributions, we introduced a novel neural memory network-based framework for future action sequence prediction tasks. To leverage both visual and action label features, we proposed a two-stream architecture. We mapped the long-term dependencies through separate memory modules, which enables better feature fusion. So by effectively capturing the information related to objects in the scene and the long-term dependencies, we propose a two-stream architecture for future action sequence prediction. So as the inputs for the proposed model, we utilize both the observed video sequence and their corresponding label sequence. And for the observed video sequence, we extract pre-trained CNN features, and then for the corresponding observed label sequence, we map them into their categorical form. Then these separate streams are passed through LSTMs in order to map the short-term dependencies within each sequence. Then we utilize separate memory networks to map the long-term dependencies. So before proceeding to the next steps of the proposed model, let's see how memory operations are performed. So I'm going to explain this only for one stream. However, the operations are identical for both streams. Let's say the memory at time instance t-1 is given by this. So this each column denotes a memory. It denotes the content of a memory slot. So given the encoder, hidden state HD theta, we generate a vector to query the memory. Then using this query, we attend to each memory slot, and using a softmax operator, we measure the similarity between the content of each slot and the query vector. Then we normalize these values. We pass these co-values through a multi-layer perceptron, which generates the memory output at current time step. So finally, using these core values and the memory output at current time step, we generate a vector to update the memory. So moving back to our proposed model, then we combine the information retrieved from the memory read operation through an LSTM layer. Then this final fully connected layer is used to generate the future action sequence predictions. So what is the importance of using neural memory network instead of LSTMs? It is a well-known fact that LSTMs fail to model long-term dependencies. The issue with LSTM structure is that there is only one hidden element for storage. So we keep on updating this with the inputs, and when the input sequence becomes too long, it loses track of all dependencies and focus more on recent dependencies. But with neural memory networks, we have multiple storage blocks. The concept is similar. We read stored information from it and determines what goes as the output and what gets written back to the storage. In order to evaluate the model, we utilize two fine-grained action datasets, breakfast dataset and 50 salads dataset. So this breakfast dataset, it contains around 1,700 videos captured at 18 different kitchen locations with 48 different actions. So the 50 salads dataset, it contains 50 different videos with 25 actors performing salad preparation activities. Altogether, there are 17 different fine-grained action classes. This dataset offer challenging evaluation conditions with different camera viewpoints and different object categories and interactions. We use Keras with Tiana backend for our implementation. So we use ResNet50 as the visual feature extractor and extracted features through Activation 50 layer. Then we evaluated these hyperparameters, hidden state dimensions, and memory lengths experimentally. So similar to the baseline approach, we also we have evaluated the model by considering different observed to predicted ratios. So the first graph in your left-hand side, it shows the results when only 20% of the early frames are taken as you observed, while then the predictions are made for the next 10%, 20%, 30%, or 50% of the frames. Then again, graph in your right-hand side, it shows the results for the same predicted percentages when 30% of the early frames are taken as the observed. Then, so the LSTM model proposed in the baseline method, it is able to achieve slightly better results than the CNN model in most cases. Yet, the results gap between the LSTM model and our memory-based prediction model is significantly large. Similar performance was obtained with 50 cells dataset. So we speculate that this significant improvement in the results of our proposed model is mainly due to the long-term dependency modeling enabled through the utilization of external memory networks. So this allows the model to learn and store the overall patterns of behavior in the memory. And when we query the memory with the portion of input frames, these stored patterns are iteratively attended and matched. So, in addition to the state-of-the-art comparison, we also performed an ablation experiment on the proposed model. So, this first model, it uses only the features from the observed video sequence, which is also known as the theta input stream, and it uses only the encoding and decoding LSTMs, followed by a fully connected layer. And the second model, it is similar to the first model, but the difference is that it uses only the observed label sequence, which is also known as the beta input stream. Then the next two models, they're based on these individual streams with the addition of a single memory module. So our final ablation model, it is similar to the proposed model with two streams, but uses only one memory component. So you can see that the addition of the memory further improved the performance of the models. And similar to the baseline method, we also observe that the input sequence or the beta stream, input label sequence or the beta stream, is the prominent stream. So this is because it makes the overall process much easier, as the model can skip the current action recognition step. However, we observe that the theta stream provides complementary information to further improve the accuracy. In order to estimate the sensitivity of the proposed method on the preciseness of the input action labels, we conducted an analysis using the action labels, which are predicted using the action segmentation model, coupled action GAN. Even though we observe a slight degradation of the performance when compared with the proposed method with the ground truth labels, still the performance is significantly higher than the baseline results. We visualize model predictions to sample video from 50 cells dataset. So the observed portion of the video is indicated in the bottom. So here we consider 30-50 split, where we observe only the first 30% of the video and try to predict the next 50%. This video poses a challenging real-world scenario where there are visually very similar actions such as adding oil, adding vinegar, adding salt, and adding pepper. However, with the advanced temporal modeling, structure of the proposed method has enabled us to automatically discover the dependencies between these actions, allowing us to achieve better performance. And it is clear that most of the model predictions align with the ground truths. So that concludes our presentation, and now I would like to take any questions you have. Thank you.
Thank you for your presentation. I'm sorry, maybe I didn't understand correctly, but what do you exactly predict? Do you predict frames or action? How do you describe your actions that you are predicting? It's an image or it's
well, the predictions are action labels.
Okay, so you have some labels that are coming with video, and after you predict that, I don't know, adding paper, adding tomato, cutting tomato. Okay, so there is a limited number of actions that you have seen, so it can predict only limited number of labels. Exactly?
Yeah.
And they should be, it cannot predict labels that it haven't seen just before or previously. It can predict the same labels that at the beginning of sequence, or no? This is my question.
It can predict future actions which I haven't seen before, but only seen when we trained the model. That's but still we can predict the ones it can see. It didn't see at the beginning.
Okay, thank you a lot.
Thank you for the talk. During the update of the memory, do you decide based on the current features how much you change the memory, or is it updated in every step, is it updated in the same way? Or
it depends on the softmax score. It depends on the softmax score that we get. So when you get with this softmax score, we decide how much of the portion of the memory slot that it goes to the next level.
Okay. All right. Thanks.
Okay.
In the next room, does anyone have a question?
No, there's nothing from this side.
No. Okay. Any last question? No. Okay, thank you very much.
Okay, thank you.
Okay, so our last speaker of the day, of the conference, is Zafeiriou from the University of Oxford.
Okay. So, hi everyone. I will present our paper, Self-Supervised Learning for Video Correspondence Flow. Okay, I will start with the overview of our method. In our paper, we introduce a method that aims to learn pixel-wise visual correspondence in videos without any human supervision. Basically, try to match semantically similar pixels across different frames. As you can see here, the helmet is matched to each other, and the handle of the bicycle is matched. So given 2 consecutive frames in the video sequence, our goal is to learn a network that can produce embeddings, such that interframe correspondence matching could be found via embedding similarities. Moreover, we aim to train the model without any human supervision, by leveraging the natural spatial-temporal coherence in videos. Once we obtain such pixel-wise correspondence, we can then use it for various downstream tasks. For example, we can take the correspondence and propagate entities at pixel level from one frame to another. Such entities could be key points or instance segmentation like this. So as an example, we show a testing scenario of video segmentation here. We could take a video and the initial mask. By using the propagation mechanism I just described, we can propagate the mask throughout the rest of the video without using any extra segmentation mask. This is the actual prediction of our model. You can see that the track is pretty good, and it shows that our correspondence is good. Next, I will introduce details of our paper, but let me start with some basic concepts. So our method learns from unlabeled videos in a self-supervised fashion. We are certainly not the first one to explore such method, because videos are good resources for machine learning, because they are there are infinite amount of data, basically. It falls under a general class of video understanding method. Many of these methods explores to learn a feature extractor, which learns meaningful embeddings so that a specific task could be carried out. We do the same. These learning tasks normally exploit a proxy task, which involves predicting part of input from other parts. Such prediction tasks could provide losses for training parameters of a model. These are some proxy tasks. So we use reconstructing task as our proxy. To put it simply, we reconstruct a fake frame 2 from frame 1, guided by the real frame 2. Then we can use the real frame 2 as a supervision. We can use this difference between this pair as a loss to train the parameters in the model. So the question is, how do we reconstruct the frame 2? So let's take 2 frames. To reconstruct an arbitrary pixel x and y in frame 2, we first match this pixel with frame 1. So we could probably match it to some pixels like this. And we take a linear combination of these pixels as a reconstruction pixel. So this is it. And we do it for all pixels to get the full reconstructed frame. At first, the correspondence could be random, but after the network is trained, we could get good correspondences. So the next question is, how can we find such correspondences? Okay, we use the same figure as before. The process goes as follows. First, we extract features from a network. Each pixel in the original frame has a corresponding pixel in the feature frames, in the feature maps. Sorry. Then we can compute the similarity between that pixel and all pixel in the feature map of the other frame. And then we can get a dense match by computing the softmax of this similarity. And this probability can be used for copying, as I discussed earlier. Next, I will introduce 4 main ideas of our paper. We show that these improvements could produce longer tracks and reduce drift. The problem with earlier method is that the proxy loss has a trivial solution. If we match the pixel only by color, for example, the red pixel here is matched to only the same red pixels. So basically a positive similarity with the same red pixel and negative similarity with all other pixels. The reconstruction would still be near perfect as the correspondence satisfies color consistency constraint. But that's unsatisfactory as we seek a high-level correspondence. We propose a simple data augmentation method called color dropout. That is, we randomly drop color channels. Color dropout uses a fraction of the input information to predict the other part, following the spirit of self-supervised learning. This augmentation could force the network to not only rely on low-level color information, but also learn to use high-level information for matching. A key challenge remaining is drifting. In many downstream tasks, we predict future frames in a recurrent fashion. Take video segmentation as an example. We propagate the mask of the car through the sequence. But notice the false positive region at the back of the car in the first frame shown. Once such an error is made, it is likely to accumulate. This is because later frames predict their masks, conditioning on the current frame. So a small error could be propagated, resulting in huge errors in the rest of the video. To deal with this issue, we propose 2 solutions to alleviate the problem. The first is training with scheduled sampling. The second is cycle consistency. First of all, during training, we apply a scheduled sampling strategy. Specifically, we use both predicted results and true frames, each with some probability, as network input for predicting future frames. In this way, we can explicitly model drifting as errors during training. As we can see in the error maps, frame 3 is predicted from frame 2. If the frame 3 prediction is predicted from frame 2 prediction, it is likely to suffer from larger errors because of drifting. By minimizing overall losses, our model makes prediction robust to recurrent predictions and close the gap between training and testing phases. Secondly, we exploit the natural cycle consistencies exist in video sequences. During training, our tracker is applied several frames forward and backward. We require that frames tracked backward is the same as the original frames. To model cycles of different difficulties, we also add cycles of different lengths. Shorter cycles tend to be easier and longer cycles are harder. Finally, we optimize the affinity matrix used to obtain the pixel similarities. Traditionally, the affinity matrix is computed for all pixels in the entire image. The affinity matrix is thus an HW by HW matrix, which demands a huge amount of memory. However, videos are full of spatial-temporal coherence, so we could use this fact and compute similarity only in local areas. This results in much smaller affinity matrix and allows a larger embedding resolution. Next, I will show some results to obtain from our method. Quantitatively, our method can achieve higher accuracy than previous method on the Davis video segmentation benchmark. Here, J stands for region J-card, which measures region overlap. F stands for boundary F measure. This is the average performance broken down by attribute that describe the type of motion in the video. Our method is shown in red. Observe a general trend of improvement over previous methods. We also evaluate performance on key point tracking with GHMDB dataset. PCK stands for the percentage of correct key points. The testing procedure is the same. We propagate the key point with predicted interframe correspondence. Here, our frame can outperform all previous method and produce performance on par with the supervised method. Qualitatively, our correspondence allows accurate mask propagation. Note we did not use any ground truths for training, and the Davis videos are also never used for training. Our model is trained on kinetics dataset, shown on the left, which is a human-centered dataset. However, as shown on the right, the testing dataset could consist of many other object classes, such as animals and vehicles. Therefore, we try to probe the upper bound performance limit of our method by fine-tuning of our model on actual related videos. For example, we use additional videos of dogs for training and test video segmentation of dog videos. We show that by using actual videos, we can improve the test performance on those specific categories. Results on more categories can be found in the paper. Our methods still produce poor performance on some sequences, which fall generally under these categories. The person on the top left corner, for example, undergoes large shape changes, sometimes leave the object multiple frames inconsistent in color, which cannot be solved by optimizing a color consistency loss. The next three videos all include foreground objects occluded by other intruding objects or go out of the screen. These occlusion-related problems cannot be solved by byte correspondences, since the tracker cannot find correspondence in the previous frame. Therefore, our method could be extended in several directions. A memory mechanism, for example, could be designed to deal with such occlusion and disocclusion problems. And a patch or object level loss could be used to facilitate object information in the embedding. Thank you.
Thanks for the talk and great work. You mentioned the cycle consistency loss. Do you only use that during training or also during inference? Like, do you ensure consistency during inference? That's my question.
Only using training.
Only during training. Okay.
Yes, because you don't have future frame masks during testing. Basically.
True, but you could do some consistency with past frames, right? To kind of improve the segmentation prediction.
Sorry, I could use consistency with what?
With the past frames.
With what?
As in, when you're doing inference, you could ensure some cycle consistency with the previous frames, right? Would that improve the performance?
I'm not sure. I haven't tried. But it's possible, I think.
Thank you.
Actually, let me ask you a question. So I was interested in your color dropout.
Sure.
Where you said you dropped out some channels, but I mean, why not just drop out color altogether and just, go for the luminance? So,
if you just go for the luminance, the problem is that during testing, the feature extraction only handles illuminance, which is information loss.
I mean, just as a dropout. I mean, not always lose luminance, but rather than drop out one channel, why not switch to luminance?
Do you mean switch the input to just luminance?
Yeah.
But then, if during testing you want to input the full color image, I don't think it would work.
Okay.
I don't think it will work. But probably worth trying.
Hi. In one of the slides, you said instead of considering the whole feature map, you consider a fixed window.
Yes.
Yes. Can you tell what was the size of the window and how did you get to that size? Did you explore various window sizes? Because it would be dependent on the frame rate of the video, right?
Yes. We use the radius as 6. So basically, the patch size is 13.
30 cross 30.
So that's like the smallest size that does not lose performance. So if you reduce that.
So 30 cross 30,
13 by 13, yes.
13 by 13.
Yes.
And
yes.
What is the frame rate of the videos that you are using?
During testing, I think it's about 12 FPS. But training, we use a random frame interval.
Mm-hmm.
You can read it in our paper.
Okay, thank you.
Let's check in the other room. Any questions?
No, there was nothing from this side.
Was that a no? Okay, last chance for a question. Okay, I think not. So, again, thank you very much.
Thank you.